Human lives can depend on the exact science of chemistry. From the familiar IV bag, salts and sugar pass into the bloodstream. They act at a molecular level so the body's cells can function again. How can we produce on a factory scale substances that work so accurately at a molecular level? How can we mix just the right amounts for the molecular world we cannot even see? To do this, in laboratory and in industry, chemists use a concept called the mole.
At the heart of chemistry is synthesis, the making of molecules. At the beginning of any chemical reaction, there are reactants. At the end, there come out products. Now, a caricature of a way of making molecules is to take the reactants, mix them together, beat on them with heat or light or some other source of energy, and then in an explosion, a flash of light and smoke, the product materializes. That's the way it goes in comic books, but that's not the way that any chemical company is going to make a cent of profit. Into any modern chemical process, there goes planning, whether it is into the making of ammonia or of aspirin or of a beautiful molecule shaped like a cube for which no use has as yet been found. Into any of these, there goes careful planning. Precise amounts of reactants have to be weighed out. Too little, and the reaction might not go. Too much, and there is going to be something left over, waste. How does a chemist know precisely how much is right?
Today, chemists know how much is right because they can count the fundamental particles of matter, atoms and molecules. It is now possible to connect the macroscopic world that we can see with the invisible molecular world. In short, chemists have learned how to count molecules by weighing macroscopic amounts. 200 years ago, scientists weren't even sure what atoms and molecules were, let alone being able to count them. For Berzelius, an outstanding analytical chemist of the 19th century, a major problem was obtaining accurate atomic masses. One needed to know how much of each element combined, the combining masses, and the correct formula for the compound. Berzelius was one of the pioneers in this effort. Nowadays, even a beginning chemistry student can calculate a formula using analytical data and the atomic masses found in the periodic chart. How has this come about? The initial breakthrough came from the study of gases. Here is a gas reaction like one they did then. 1 volume of hydrogen gas is released into a clear balloon. Then 1 volume of chlorine into another balloon. The valve is opened so the two gases mix together. When a light is shined on them, there is a chemical reaction to form 2 volumes of a new compound, hydrogen chloride. Note 1 volume plus 1 volume produced 2 volumes. As you know, chemists learned that all gases react in small whole number ratios. What principle lay behind this gas law, stated in 1808? What is happening at the molecular level? The Italian scientist Amedeo Avogadro pondered these questions. In 1811, he proposed that equal volumes of different gases at the same temperature and pressure contain equal numbers of molecules. Now we understand Avogadro's insight. We know why gases react with each other in simple ratios. A molecule of chlorine gas is made of 2 atoms, and a molecule of hydrogen gas is also made of 2 atoms. When the gases combine, 1 volume to 1 volume, 2 volumes of the hydrogen chloride molecule are produced. In gases, there is a simple relationship between numbers of particles and volume. Therefore, if we measure the mass of equal volumes of different gases at the same temperature and pressure, we can easily calculate the relative masses of the molecules, since there are an equal number of molecules in each case. So, in gases, the determination of relative masses is quite straightforward. But determining the relative atomic masses of solids and liquids requires more ingenious methods. Let's take a closer look at the problem of the relative masses of solids and the notion of counting by weighing. Don Showalter.
We have in front of us here a balance that chemists use to weigh chemicals. The weight will be read out here in grams. However, rather than just weighing chemicals, let's weigh something we all like. Let's weigh some money. I have a quarter. 1 quarter weighs 5.7 grams. Let's weigh 1 penny. The penny weighs 2.5 grams. If we wanted to determine the relative weight of the 2 coins, we would divide the weight of the quarter by the weight of the penny. If we do that, you see that we come up with a value that shows that the quarter is about twice as heavy as the penny. Now let's weigh this pile of 20 quarters. It weighs 111.9 grams. Now let's weigh this pile of 20 pennies, the same number of pennies. The weight is 51.0 grams. If we would want to determine the relative weight of the piles of quarters to pennies, we would do that in the exact same fashion as we did with the single coins. And you see that that ratio comes out the same. The same principle of relative weights that we've done with the pennies and quarters applies also to the molecular world, even though we can't see molecules or atoms. I can't pick up an atom or a molecule and put it on that balance, but I can pick up a huge number of atoms or molecules and weigh them. Now here is something we can see and weigh. It's the element carbon. It's this black powder in here. Let's see how much this carbon weighs. We'll put a dish on there to protect the balance and cancel out the weight of the dish. And we weigh the amount of carbon. It's 12.0 grams, an important weight to remember. If we wanted to compare the weight of another element with the weight of carbon, we would have to have exactly the same number of atoms of that element as there is in this 12 grams of carbon. Just as we did with the quarters and pennies, we had to have an equal number of quarters and pennies to compare the relative weights. What is the number of atoms of carbon in that material, 12 grams of carbon? That number is what the chemists call a mole. A mole is the chemist's unit of measure, just as the dozen is the baker's. The mole isn't a single molecule or a single atom. It's a huge number of atoms or molecules, and it's always the same number. Just like the dozen is always 12. But the mole is much larger than the dozen. It's 6.02 times 10 to the 23rd. That's what we call Avogadro's number. How big is Avogadro's number?
A molecule is so small we can't even see it. But if it were the size of a single grain of sand, 1 mole of sand would cover a city the size of Los Angeles, 600 meters deep. So, the mole is a unit of measurement. It's a number, an inconceivably large number. It is determined experimentally and not by counting. Can you imagine that a computer counting 10 million atoms a second would take 2 billion years to count out 1 mole? The mole allows chemists to count molecules and atoms by weighing the mass of vast numbers of these particles. This is a mole of copper. This is a mole of water. And this is a mole of hydrogen gas. All have different masses, but each contains exactly the same number of particles, trillions and trillions of them, but exactly the same number, Avogadro's number, 1 mole. The mass of a mole of any element is equal to the element's atomic mass expressed in grams. These are the relative atomic masses of the elements in the periodic table based on assigning carbon a mass of 12 units. Let's use the periodic table for some examples. Here's copper. Its relative atomic mass is 63.5. A mole of copper weighs 63.5 grams. Let's see another element. Here's magnesium. Its relative atomic mass is 24.305. A mole of magnesium weighs 24.305 grams. The same principle applies to compounds. Here's a water molecule, H2O. The relative atomic mass of oxygen is 15.999. The relative atomic mass of hydrogen is 1.008. If we add these atomic masses together, 1 mole of water will weigh 18.015 grams.
And so we see how we can go from the number of particles to the number of moles and then to the weight of a substance. Now we have some real live moles. Each of these substances is a mole: sugar, water, carbon, copper, and hydrogen. They all have different weights, but they all are made up of Avogadro's number of particles.
The mole, then, is the crucial link between the invisible molecular world and the chemical elements and compounds that we can see and measure. Through an understanding of the mole, the chemical equations used to describe reactions represent an extremely informative kind of chemical shorthand. This equation tells us the number of molecules that react and the number of molecules formed, the number of moles that react and the number of moles formed, and using the relative atomic masses, the weights of the reactants and the products. With the mole, chemistry has become an exact and quantitative science. The largest manufacturer of intravenous fluids in the world is Baxter Travenol Incorporated. As in other chemical plants across the country, chemistry is carried out here on an enormous scale. IV solutions are prepared by pouring bags of chemicals, in this case the sugar, dextrose, and salt, into a huge mixing tank containing distilled water. There is little room for error. The cells in our body depend on precise molar quantities of molecules and ions to function correctly. The wrong balance can destroy those cells. So, each batch of IV solution has to meet exact medical specifications. Chemist Johnny Long.
We have many codes registered with the Food and Drug Administration. The one we're mixing today is a salt and sugar combination batch, which contains 4.5 grams of sodium chloride, or salt, per liter of distilled water, and 50 grams of dextrose, or sugar, per liter of distilled water. These weights are added to a known volume of distilled water in our mixing tank.
Quality control is vital. Before the IV bags are filled, a sample of the solution is withdrawn and analyzed to make sure the correct amounts of sugar and salt are present. This is where the mole comes in. Here, the chemist is analyzing the amount of sodium chloride in the sample. The procedure involves titrating a sample of IV solution with a standard solution containing 1/10 of a mole of silver nitrate per liter. Let's look at the equation for this reaction. We see that 1 mole of silver nitrate reacts with 1 mole of sodium chloride to produce a white precipitate of silver chloride and soluble sodium nitrate. Using a burette, which makes precise measurements of volume possible, silver nitrate is added until all the sodium chloride has reacted, as shown by the color change in the indicator. The chemist then reads off the volume of silver nitrate added, from which she can calculate the number of moles used, which equals the number of moles of sodium chloride present in the sample. This number can then be expressed in grams of sodium chloride per liter of IV solution. A comparison with the specifications tells the analyst whether or not the IV solution is within acceptable limits. If so, the tank solution is released to fill the IV bags.
This is one of our IV bags. As you can see, our label for this particular code states that each 100 milliliters contains 5 grams of dextrose and 450 milligrams of sodium chloride.
That label translates back to the mixing process and the careful analysis. Counting by weighing. The mole is ubiquitous in chemistry. It gives us a window through which we can glimpse the molecular changes that accompany chemical reactions.
Remember that original question? How much of which? Well, to see what that means, let's perform a chemical reaction. In these 3 flasks, I have equal amounts of hydrogen chloride dissolved in water. Each one contains 1/10 of a mole of hydrogen chloride. Each of the balloons have differing amounts of magnesium. This balloon has 1/10 of a mole of magnesium. This one has half as much, and this one has 1/4 as much. I will empty the magnesium into the hydrogen chloride, form magnesium chloride, and generate hydrogen gas. That will blow the balloon up. Which one of the balloons do you think will inflate the most? The one with the most magnesium in it? Well, let's try it and see. We'll introduce the magnesium into the hydrogen chloride. You see now that hydrogen is being given off. The balloon is inflating. Well, let's start the other ones too. Again, you see hydrogen gas giving off. Magnesium chloride is formed inside the flask, but it is soluble in the water, so we really don't see it very much. Let's try this one. And remember, this one had a small amount of magnesium in it. This one had the most, 0.1 moles. This one had half as much, and this one had 1/4 as much magnesium. The reaction is completed. These balloons are very much the same size. This one's only half the size. We can explain the difference here because this had half as much magnesium as this one. But why are these 2 balloons the same size?
The answer lies in the chemical equation for this reaction. For every 1 mole of magnesium, we need 2 moles of hydrogen chloride to complete the reaction. Here are the results of our experiment. The green balloon had equal mole amounts of magnesium and hydrogen chloride. The hydrogen chloride was used up, but a lot of magnesium was left over. In the flask with the yellow balloon, the ratio was twice as much hydrogen chloride as magnesium, which is the 2-to-1 ratio we needed for the most efficient reaction. In the flask with the blue balloon, there was too little magnesium to consume all the hydrogen chloride. The result? Less hydrogen gas and less inflation. When molecules or atoms combine during a chemical reaction, they do so in simple molar ratios. In the magnesium-hydrogen chloride reaction, this combining ratio is 1:2, exactly the amounts present in the reaction with the yellow balloon. The additional magnesium in the green balloon does not change the amount of hydrogen gas produced. Without a corresponding increase in the amount of hydrogen chloride, the additional magnesium remains unreacted. Chemists must use the correct number of moles of reactants in a reaction in order to get the desired amount of product. Sometimes, the molar ratio also determines the kind of product. If you use an inappropriate molar ratio of reactants, you end up with a different product. Take epoxy resins. We use them in our homes as adhesives. Due to their unique combination of properties, toughness, excellent strength and adhesion, and resistance to other chemicals, they are widely used as coating and structural materials. Food and beverage cans are coated with epoxy before the contents are added, so as to protect them from the metal. Fighter jets are held together with epoxies. Even computer circuit boards are made using epoxy. But their properties depend on their molecular structure, and this, in turn, relies on combining the correct amounts of other chemicals. Here at Dow Chemical in Freeport, Texas, an important class of epoxies used as coatings is made by reacting liquid epoxy resin of low molecular mass with bisphenol A. The object is to have the two combine to form large epoxy molecules, each with a very high molecular mass, in a process called polymerization. The higher the molecular mass of this epoxy, the more desirable its properties. The relative amounts of each reactant are crucial to this process. John Massengill is a research and development chemist at the plant.
In order to build the maximum toughness into our final coatings, we combine liquid epoxy resin and bisphenol A in equal numbers of molecules, and this is where the mole concept comes into our practical world of chemistry out in industry.
Massengill uses the mole to convert numbers of molecules into mass.
From the mole concept, we know that using the molecular weight in grams of each of the combined materials, we can get equal molar quantities. So in terms of the liquid epoxy resin, the molecular weight is 343. So we use 343 grams of the liquid resin. With the bisphenol A, the molecular weight is 228 grams. So the combining ratio is 228 grams to 343 grams. When those are reacted in those ratios, we will get a very high molecular weight.
During the production of this epoxy, samples are taken and analyzed by the quality control lab to make sure the product has a sufficiently high molecular mass. This analysis involves titration. Once again, the mole comes into play, allowing the analyst to equate numbers of moles with mass. Too much of either reactants results in an unacceptable product. Only by combining equal numbers of moles of the liquid epoxy and bisphenol A is a solid epoxy resin with the correct properties produced.
So using the mole concept, we're able to, in the laboratory, in the real world of chemistry, to measure out numbers of molecules that we need for our chemical reactions.
No matter what the scale, the mole helps us understand chemical change. It points to the essential arithmetic that accompanies all chemical reactions. It tells us how much we have and how much we need. To review, modern chemistry is a quantitative science. During chemical reactions, molecules, atoms, and ions, those unimaginably tiny entities, combine in exact whole number ratios. Chemists have found a way of counting these particles, not individually, but by weighing huge numbers of them. The counting unit is the mole, Avogadro's number, 6.02 times 10 to the 23rd. Whether a gas, liquid, or solid, element or compound, 1 mole contains that enormous number of particles. The mass of 1 mole of any element is equal to the element's atomic mass expressed in grams. 1 mole of a compound has a mass equal to that compound's molecular mass. The mole allows chemists to move between the invisible molecular world and the macroscopic world, whether in medicine or in industry, in the lab or in full-scale production.
The mole, a simple idea, many practical uses. Imagine you're a farmer. You've cut down an acre of corn, and in that corn are 6 kilograms of phosphorus needed by the plant, essential to us. So you know you have to replace that phosphorus in the soil before you plant. You go to the store, and you see a fertilizer called superphosphate. You read calcium 3, phosphorus 2, hydrogen 14, sulfur 2, oxygen 21. How much of it should you buy? A pound? A ton? The simple arithmetic of the mole tells us how much. Or imagine you're a chemist. I'm a chemist. Someone tells me to make some titanium disulfide, TiS2. Do I take a gram of titanium and 2 grams of sulfur? No. I take a mole of titanium and 2 moles of sulfur. What's important about this is not that an expert, a chemist, can figure it out. It's that others can. You can. Think about that.